It'll be up and running, right? You're gonna wait for all the late people. You're gonna wait for them.
I don't know. Is that great?
Go ahead.
Okay, so thank you everyone for joining today's seminar session. It's my honor to introduce Professor Walter Thomas Donner. He received his bachelor in mechanical engineering at Worcester Polytechnic Institute in 1983. He received M at Boston College in 1989. He received technology at Worcester Polytechnic Institute in 2001, and he received his second Master of Manufacturing Engineering at Worcester Polytechnic Institute in 2003, and he received his PhD at Polytechnic Institute in 2013. Professor Tanner has been director of WPI Center for Innovative Manufacturing Solutions since 2015. He is interested in manufacturing and industrial engineering. His main interests lie at the intersection of manufacturing process and the financial aspect of the business that relates to these processes. He sees his mission and helping them extract value from the process that drive the organization. His research team do this by using tools like axiomatic design and Lean Six Sigma methods. He likes to frame the lecture in such a way that the students picture themselves in the field, supporting or leading members of the organizations and having an immediate impact on the operation. Professor Walter.
Thank you very much.
Thank you.
Hey, good afternoon, everybody. I'm going to tell you a little bit about myself before I get going. I grew up in a manufacturing family. Did a lot of welding, laser cutting of metals, bending of metals. So I know how to run press brakes. I can weld. I used to own one of the largest laser cutters in the Wingwood at one point. Designed a lot of things for customers that were trying to get things fabricated. And just generally have a pretty long background of being involved in manufacturing. Fast forward up to about 10 years ago, and I come to WPI and I become a full-time university professor after my PhD advisor, Professor Christopher Brown, earned my PhD. And I have a really cool job because no one in the business school where I work knows anything about what goes on over in manufacturing engineering. So whenever I tell them, they say, oh, that's very cool. And then the people that I work with over in manufacturing, they have no idea what goes on in the business school. So whenever I tell them, they say, oh, that's really cool too. So I'm in this really interesting space where I can pretty much do whatever I want. And no one knows what I'm doing. Professor Brown, over the years, has encouraged me to bring this axiomatic design thinking that was developed by Professor Su back in the 70s and 80s and into the 90s. And I try to introduce this hierarchical way of breaking problems down in the business school. So I'm rather unique in that sense that a lot of the business school professors have engineering undergrads, but they don't have very much experience in design theory or design methods. And I try to have as many of my major qualifying projects use the axiomatic design method to do problem definition. And so Professor Brown and I have been going back and forth now over many, many years about how I use it and how it's a little bit different than what he does. I talk to the students, and what I want to know from them is, can you define the problem that you're working on? And what does every engineer say? Oh, absolutely, I've already figured it out. I said, well, how have you figured it out? You haven't even tracked anybody that's been affected by what you're working on. So could we have a rigorous examination possibly a hierarchical decomposition of what we actually think we're working on. And then maybe I can see if I agree with you, and maybe the sponsor agrees with you, and everybody in the project agrees with what you're working on. And if someone from the outside looks at your work and they tell what you're working on. And so I have a lot of fun with this, as you can tell. Some introductory slides. First, thoughts on axiomatic design. So when I took MFE 520, I think the number's different now. It was primarily a manufacturing process design course and crossed into a mechanical design course. Very little on business directly. I mean, we might want to find out how much something costs or what it's worth, but breaking down the business elements is not really a part of that course. It's very much in the physical world. And I have come to find over doing many years of MQPs and MFE that it's often easier conceptually to do the MFE 520 course than it is for the IE majors and the operations management majors to work on problems. Because in general, engineers have these very fixed constraints. You can't make a jet engine that runs at 90,000 degrees because there's no materials around that's going to do that. And Mother Nature tells you what you can and cannot do and where the limits are. And so, of course, we're always trying to find some workarounds to make our designs work out. But in the business sense or industrial engineering sense, they're all human design systems and they're only limited by your imagination. And we can think about a lot of major businesses affecting the world today, like Amazon. Amazon said, well, we're going to have very fast delivery and low expenses and set up a new paradigm and basically knocked out all, these businesses all over the world. The constraints on Amazon and how they put that business together are really very, very different than what an engineer would feel as if they were trying to design a device, an engine, some kind of mechanism. And so I think about that there are natural constraints, and I've talked to Professor Brown about this a number of times, that we really ought to write a paper on this, because my perspective is that engineers come up against hard boundaries that are imposed from the outside, limits on property, of materials, in every sense, right? Thermal properties, whether you can stress loading on things. And we don't really see that over in industrial engineering, operations management, and management engineering. So boundaries force, or with natural boundaries, forces deep analysis on workarounds. So, for example, I know Professor Brown's been working on the product she was working on to reduce forces in the need to prevent ACL injuries and other kinds of injuries. And my cursory examination of what he's working on is that Mother Nature tells him a lot what he can and he cannot do. How strong springs can be to resist forces, how strong kind of forces your knee can resist when it's being under load. He can't just wave those away. Business situation, we have a lot more latitude. And so I think of them like boundaryless problems. So I have this role as a teacher and a project advisor doing MPs. The engineers, especially the undergrads, don't like squishy solutions, right? They want a right answer. Give me a grade. The answer's 100. Give me a grade. And how things tend to be determined as probabilistic are not as satisfying to work on, because we want the right answer. And so, especially in industrial engineering and in the management students that I have, the answers are very squishy. Right? They don't have very concrete, singular numerical answers to problems, and they look like a recommendation more than they look like a solution. So rarely anything's fixed in the world that I live in over there in the business school. Or constraints are self-imposed. You could have a self-imposed financial limit, self-imposed limit of timing and how long we need to allocate to do something. But then again, these things are adjusted. So it's not exactly like working on an engineering problem. So I've come down to think about this Mother Nature's hard limits or hard constraints versus more boundaryless problems that I see in these MPPs. So why use axiomatic design in a method as a method to do problem definition when we can presumably skew our analysis to get any common outcome that we want? Well, it's clarity. And one of the things I learned studying under Chris was that Sue's axiomatic design method is as much of a communication tool as it is anything else. It's very transparent. So if you'd like your superior at work or your peers or your charges that are attending to you or outside investors to understand what you're thinking, let's show them a decomp. Let's shoot it up in the wall and let's talk about it and expose this. And many business folks do not naturally gravitate to that very, very in-depth defined problem management perspective. Okay, so when I'm teaching my undergraduate MPPs, I tell the students, so it's an end of A term, which I have a lot of MPPs that start A term, and I say, the only thing I need from you by the end of A term is a decomp. I don't really even need a presentation. I just want to know, can you define what this MPP is about? And it takes them the whole term. Sometimes it takes them more than the first term. Once you have worked through this decomp, you've solved your OMQP. You can solve any problem once you can define it. The problem is we don't define them well. And so we solve something that's not the exact appropriate problem that we're hoping that we were going to accomplish. And it drives them crazy, right? Because they want to just, leap to a solution. And I said, well, you can't do that until I agree. And I think that's what you're working on. If we have an outside sponsor of the company, that they agree that what you're working on. So over the years, from when I first started teaching and now I get up to this point, I've learned the value of really forcing to do this hierarchical decomposition. And I tell the students that after graduation, how do you move up the chain of management? Never be wrong in anything you say. Well, how do you do that? You do a really dumb definition so that someone can't say, well, I think you missed something, or I don't understand what you're saying. So it's all in my decomposition here. So get better outcomes. My BUS 3020 Achieving Effective Operations course runs ABC terms, has a lab in it. The first one-piece flow lab that we use. That is the first exposure to lean coupled with axiomatic design that I do. And so this is the first slide of the first lecture of the day in that course. How do you make money with this process? So the undergrads look at this. I would think most of you in this room know what we're looking at. But I would say, what is this? And then they give up. They don't even try. I don't know. That's Star Trek, Space Age, Star Wars. I have no idea what it is. And I say, well, is there any evidence? Is any energy involved in this? Okay. Do we have any kind of material things happening? Obviously, it's on some kind of a machine tool. So that lends you to think, well, do we have a whole year to make this part? Or do we have to make it in 10 minutes? So that implying you got a load unload time. And so I work through this with them. And I try to get them to understand that in any manufacturing problem, or almost any problem we can describe in general, and this is also from Professor Brown, is maximize the value added, minimize the cost. So then once I throw that at them, they start to think about, what is value added? And how you can measure it. Can we tell when we're doing it and we're not doing it? So I used to own this equipment back when I was an industry guy. And so if our top level function requirement is increase return on investment from laser cutting, well, the only way I'm making money with the laser is the beam's on. If the beam isn't on, I'm not making money. I don't know what I'm doing, but it's not making money. And then once the beam is on, and in every other case, I want to minimize the cost of operating the machine. If I do those two things, I have a nice bank account. Better than the guy down the street that doesn't do that. So this is a screenshot of the Aclaro software, which apparently is elusive to find on our campus now for some reason. And so what's great about the Aclaro software is when you make the coupling matrices up, it's much easier to handle them in Aclaro than if you do it in Excel or Word. But be that as it may. And so if I ask the students, I say, well, if we increase the return on investment from laser cutting, what are the top three things we need to do, or the top things in total that we need to accomplish that? And we agree that, well, we have to increase the throughput rate of whatever the parts are, maintain the quality, or we can't sell it, and reduce the cost. And if we do all those three things, it adds up to, we're making more money with the laser cut. So all these things can be decomposed. I'm sure almost everybody in this room and listening to me has been through the axiomatic design course, and so it should be very familiar to see this. And I always found a slide like this is interesting, is that is there an order of adjustment of running the laser machine? You say, well, obviously we can't reduce the cost before we fulfill FR1 and FR2, because we just shut the laser off and go home, and the cost us nothing to run the machine, right? But we don't accomplish FR1 or FR2. So we have to do FR1, the DPs affect FR1 and FR2 first, and then we can think about reducing the cost, right? So this is a little more detail. I'm not going to spend too much time on that, but it just shows how things are decomposed. And I share this with the students. We do have some coupling deep down where the way that the laser works, the energy and the motion system, that there can be a little bit of going on to get it to be fine-tuned. That's not easy to avoid. But they're industrial engineers, they're operations management, they're management engineers, and they say, well, why did we break this problem down using this hierarchical decomposition? I say, because we need to understand the interactions between the way we're solving our problems and the goals that we're trying to achieve. And it turns out there are three actors in this system. The operator influences certain function requirements because they're running the machine. And that operator is responsible for load unload time, so they can do it quickly or not quickly. They could run the machine at its fastest speed or not, or too fast. The laser is another word for Mother Nature. Mother Nature says, hey, you got 4 kilowatts. And I don't care how fast you want to go through that 3/16 stick stainless steel, you're only going to go at 7 inches a minute. Because if you go at 8 inches a minute, you don't have enough energy to vaporize the material, and you're going to have all this molten bubbly stuff on top of the surface, right? But why don't we cut at 6? Oh, we could, but then we leave some money on the table because we could actually do our processing at a faster speed and maybe get a higher throughput. And so you get this trade-offs. But Mother Nature, being the laser, tells you, and Mother Nature influences us in different ways in this too, in that if we're going to make a 1-inch square hole under very high speed, it turns out that because of inertia, and F equals ma, that as the laser starts to position the table and material, it cheats and it cuts and starts going the opposite direction, because the computer's telling it that, you know, there's a direction change coming up. You cannot run the machine all the way into the corner at 1,000 inches a minute and then instantaneously go 1,000 inches a minute this way, because something's going to break. So through a look ahead, the machine will cheat on that and start to sneak around the corner before it gets there. So you have squares that have round things in the corner. Now we can avoid that by looping the corners of things, right? But so there's a lot of interesting things that the laws of physics come in that influence how productive you can be from an industrial engineering perspective. And then we also have someone who sits up the other end of the building in an office connected to the machine with a wire or a cable or wireless, and they're writing programs to make this machine do what it's doing. And if you have a lot of holes in a sheet of material, do you want to cut one hole in one corner, one hole in the other corner, and go over here? So we got 19 miles of motion on the sheet. We haven't cut anything. We want to have some kind of predictable way to do our tool path, right? So, but if all these three things are not interacting with each other in an intelligent way, we leave money on the table. So that's the point of this. Show the undergrads. This is we're up at Saint-Gobain. Saint-Gobain is making diamond grinding wheels. They press the diamonds around the outside of these wheels. They're all custom made, and their lead times are excessive. And so this was a group of industrial engineers. You can see their majors up here, one management major in here. And what they have done is they take these Toyota's 7 ways of manufacturing, Timwood, patient inventory, motion, meaning human motion, wasted waiting, overprocessing, overproduction, and defects, and then they will put that into a hierarchical decomposition to see if they can tease out where there are unwanted interactions between the design parameters of how the production system is being fulfilled relative to the goals of the production system. See, this was a company over in Hudson, Mass. that made special optics that go into satellites that were ridiculously expensive. And they're finding that prior to putting on the last coating of some optical thermal coating on this thing, whatever it was, that because the surface was not prepared, it was not able to accept this coating, and they would have a defect and have a do-over on these very expensive optics. And so by analyzing the company's processes in the shop, and they identify that one of the methods they're using affect 4 functional requirements at the same time. They're saying that when we propose a solution to the company to improve this application of this optic film, that we have got to resolve what this design parameter is doing to avoid not being able to fulfill these goals properly. Okay, this one I had, now this is interesting. Many of my MPPs come up where we have an uncoupled matrix. So we have this nice diagonal, you know, you got an A for that, and MFE 520, everything's uncoupled, and there's like no problem. That does not happen in MFE 520 very often, but in the business world and industrial engineers looking at processes, you'll find that whatever the functional requirements are for the business or the system, and we understand what the design parameters are, they often end up all being completely independent from each other, meaning that you can change any of the design parameters of the system independently of each other and not affect another DP or not affect another FR. And so why would we want to apply axiomatic design if this happens so often? And we get into this concept of collectively exhaustive and mutually exclusive when we're making our functional requirements list. And so the students frequently will have very highly detailed functional requirements that respond to customer needs. They have highly detailed list of design parameters to fulfill them. And this list needs to be collectively exhaustive, meaning they didn't miss any. And they are mutually exclusive so that we don't state something 2 different ways and add an element of inefficiency into the decomposition. So even though we may know intuitively in advance that the design parameters and the functional requirements are going to have a basic 1-to-1 matching, it's still very helpful to break it down because we know we haven't missed anything. Okay, let's see about this. This was an MPP of the FlexCon, and here we see again that we have all these independent. When you're explaining this to the workers on the shop floor of doing some kind of process improvement, this is a very nice company where they actually have things out the shop floor that show dwell times, run times, utilization ratios. And so you have these college students coming in from the outside who know they're very smart, but they don't know a whole lot exactly about what the process is. And for them to be able to go to company management and say, we think these are what you're trying to accomplish with this process. And we think that these are the methods you're using to do that. We've noticed that these are all independent. Have we missed anything? Collectively exhaustive, mutually exclusive. And if we look at whatever functional requirement that's not being fulfilled, something's taking too long, or there's a reject rate associated with it that's not acceptable, then we know exactly what we're looking at rather than having things less defined. So this is a larger view of that axiomatic design decon for that particular one. All right, so that's kind of at the undergrad level. If you look in the library, I don't know how many MPPs I have about now, 60, 70, something like that. 3/4 of them easily have decons. And when the students come into my office, I had a really interesting conversation with Dean Jackson last week. Dean Jackson, Dean of our business school, who's just an incredible person. Student said, "Will you be my MPP advisor?" Yes, but she doesn't know how the system works because she's never done it. She doesn't know how to make the paperwork work, go in there and register a project. I said, "Hey, I'll co-advise with you. And then after that, you'll know how everything works." And she said, "Well, what do we do in the MPP?" And I said, "Well, my MPPs, which, you're the dean and can figure out what's important to you. But I only care about two things in my projects. One, can you do problem definition, which we talked about, and can you explain the financial ramifications of whatever solution in quotes is to the project? And whatever happens in between, I don't care. If we're looking at a manufacturing process, we're looking at, I have one running in Guyana now, where they're looking at farmland they're trying to bring online. There's one coming up in Ghana, which is the one that Dean Jackson's involved with. The student's going to go to Africa for sea term. And I said, I know a lot about, a little bit about a lot of things. And so I do not profess to be an expert of the content of any particular person's FUP. But what I do know is when you walk across the stage of graduation and you go to your first job, I know you can do a very good job of breaking problems down through this hierarchical decomposition problem. And I also know that you can represent the value of yourself to your company because you can explain how the company is going to make more money or how the company is not going to lose money, because you can speak that financial language to some degree. And anything that happens in between, that's good, important, you should know that. But the two skills I want you to be able to do, problem definition and understand the financial ramifications. So I shared that with Dean Jackson. Moving into teach the axiomatic design method in just about every course I get the chance to do it. But those students are different than the undergrads. And say age, and I mean age, I don't necessarily mean, an experience thing. It's more about, possible. Someone who just graduated from a program will go to a company, they can think they can do anything, turn the company upside down. And someone that has been in for like that's not going to happen, right? Look at General Motors going bankrupt back in 08. And then you have the experience piece of it, what their job responsibilities are. We have lots of international, what the undergraduate degree was, what the problem they're working on, and all kinds of things. And the axiomatic design levels the playing field. So we can have any kind of combination of these people work to collectively, collaboratively on a technical problem, and everybody knows what's going on with everybody else. It just levels the playing field. Now, can you use this at work after you graduate? You definitely can. You may not want to tell people it's axiomatic design, which gets Mrs. Brown mad. Why not tell them? I said, because you can walk in and you got some secret thing they don't know about. They don't want to play in your sandbox. So you grab a marker, write on the board. Is this what our goals are? Oh, here's how we're solving the problem. And do these things affect more than one goal at the same time? And they'll say, "Oh, you're so smart. Gabby, you're so smart." Don't call this axiomatic design, right? Because then they think you parachuted in from outer space and have all this special stuff, right? Okay. Work is driven by a corporation that's got a problem. It's not just a theoretical coursework problem, but it's costing somebody some real money. Student frequently is the only one that knows what axiomatic design is. So ambassadorial role, or they actually may be thwarted. And that's the other people in the company don't want to hear or understand this, whatever this person's talking about. So they're in a very different role. The student has to perform the problem definition from a much more truly consultative perspective. And I have a couple of examples I have going on right now. Before I get to that, I will share with you really quickly my initial foray into using axiomatic design to solve process problems that were not necessarily, welding and machining oriented. Title of my dissertation was the design of engineering as a manufacturing system. And part of that dissertation was to understand how to efficiently educate engineers. So if WPI were a manufacturing production system that produced college degrees in engineering, which it is, what does WPI want to be able to do well, maximize the value added? Because every other engineering school is trying to do that, and minimize the cost. And we're not sure any engineering school is trying to do that, but it's a good idea, maybe. And so a number of years ago, the association, the accrediting board for engineering technology, these people up that come around, snoop around the school, make sure that we're teaching the right thing. They said, hey, there's this A through K list. I compressed it to fit it on this slide. But they say engineers should be able to design, they should be able to solve problems, be aware of lifelong learning, like this A through K thing. And that's the value added. Because who determines whether WPI is any good or not? Currently, it's ABET. And they come in and they say, well, hey, the school is meeting all this criteria we set, and give them the gold seal of approval, and can, we'll come back in 5 years and make sure nothing's changed, right? Because that's pretty much the only group that looks at universities. And then from my manufacturing engineering perspective, I look at the Toyota production system, the Timwood transportation, inventory, waste, and weighting, apply that to the system that the engineering schools operating to create the engineers. I actually added a couple of extra ones. The Timwood thing is not exclusive in that you can actually have extra or additional wastes. And so an unleveraged professor and an unleveraged infrastructure, like why is this classroom being used at 3 o'clock in the morning? Because it's here and it's heated and it has all this stuff. But that's a question for another day. So I broke all this stuff down, spending a year working on this hierarchical decomposition with my wonderful PhD advisor, and finding out we got coupling all over the place. So if you were in charge of setting up a system to educate engineers, the people that come in and evaluate you really don't have a very clear way for you to understand what they want you to do. Because they don't have a collectively exhaustive, mutually exclusive list. So I'm going to cruise through this really quickly. I did 17 different kinds of figuring coupling out, sequential, intended, FR coupling, all kinds of coupling, which was very much a foundational component of my PhD study. And I suggested that, well, if we're going to run an engineering school and create engineers, we want to say, well, they have to have factual knowledge, 32 feet per second squared, got to kind of know that. Knowledge of consequences. If I pour oil on the ground, it's going to maybe go in my name as well, right? Then you got the whole engineering skills thing using MATLAB or whatever. And you got to be able to write a letter and talk on the phone and work with people, right? And so if you notice, all these A through K fit into one of these buckets. And then our system that we're going to use to design our engineering school, we have this nice uncoupled matrix, which is actually greatly simplified with, with just having 4 FRs now. And so I wrote this up and sent it off to ASEE, American Society of Engineering Education. They said, don't ever send us anything like this. But the new ABET criteria, they reduced the A through K. I think there's 7 of them now. Like, they plagiarized my paper. No, they did not plagiarize my paper. But I think they understood too, that it's just very confusing. Everyone wants to put the kitchen sink into some specification. And then when you try to pull it apart and unwind it, you can get confused as to what is really important, right? And here again, we see it's a bit running the WPI as a manufacturing system. You should, theoretically, be able to adjust every design parameter independently of each other and only affect one effort at the same time, except that this one, which you can't see because I don't have room on the slide, this is a reduced cost. But you can't reduce cost unless you fulfill all the other FRs, and then reduce the cost, same as that laser example I gave you earlier. So I've been thinking about this now for 10 years, and Professor Gonzalez and myself have been taking a much more business-oriented approach to challenges of universities being able to run efficiently. So it's a twist on my PhD. My PhD was very much from the student's perspective of why does it take so long to graduate from college? Because there's a lot of non-value added time the students don't control. And if we could give that control back to the students, they could achieve more in that time. COVID has helped that a lot, actually, in that taking online classes, you very much can control your time in class, right? But back on campus together, you're at the mercy of whatever the university campus. And so I said, okay, well, let's look at it from the universities. What are the FRs for the president of the university and the provost and the department heads? And there are also additional customers of this system. If I were a student and you'd like to go at your own pace, meaning that how many times have you been in a class? You're like, I want to go faster, I want to go faster, I want to go faster. You can't go any faster than the syllabus says, unless you have an enlightened professor such as me that says you can finish my course as fast as you want. And you can do something else with your time. I'm not going to penalize you and make you just sit here. So we can get at that with OMP's flow model, which also came out in the dissertation. You got to learn the academic content, obviously, and you want to have timely feedback so that you know what needs to be improved upon on your end. If I'm a professor, I want to give good content, and content's easy because you just go to Google, the whole world is on it, right? I can lecture to 1 million people. That's a walk in the park. I can't answer questions from 1 million people. We need a system to get derogatory from the students back to the professors so that the students are getting the experience that they need. And the administration would like to have one professor for every 50,000 students, would be really ideal. So you get good leverage, right? But you know, there are limits to that. There's also, think about this in the inverse sense. You could have 4 teachers for 1 student. So if you were the king of a country or something, you could have, you know, 4 students for every subject for your child. Very inefficient, highly, you know, quality oriented, but expensive, right? So what's the right number of this student teacher ratio thing? Especially with schools having challenges meeting operational expenses, and next year is probably going to be even more. So we're putting this decomp together. We're back to Professor Brown's manufacturing engineering axiom or law, however we want to think about that. Maximize the value to the product, which is the education process, minimize the cost of the production process. And what's interesting is there are systems that actually the cost is 0. If you want to learn how to drive a car, you go online and they teach all this stuff online and they pay for it, right? But the value of the experience and the outcome of the student may actually be very low because you don't have any kind of feedback system. So we want to instruct the students efficiently and do it, and then you need an operation to do that. So broke all this down, and I just lectured on this in Atlanta about 3 weeks ago. And so universities have the ability to change any one of the methods that they deliver the system relative to the goal. Because things can be very confusing if we change too many things all at once, especially in a university setting, because professors generally don't like to be told anything at all. They say, well, here's a new idea, way to teach a class. And they go, no, I'm not doing that. And you can't make me. So they say, well, the school needs help financially to run and be more efficient. And the professor says, well, it's not really my problem. You're the administrator, you fix it, right? And so that when I saw a lot of schools go out of business over the past few years because of what COVID did to them, I'm thinking, well, how could they have avoided this by reducing their expenses? I developed a value stream map to go along with that model. This is the way a course looks now. And if you go from 20 to 40 to 60 to 80, 100 students, now the instructor is drowning in fact, we have that happening in computer science right now, right? You got courses that have 160 students in them, and the professors can't go to bed at night. They have, it's like the Matrix, and they got this thing jacked in the back of their head, and they're plugged in 24 hours a day trying to manage all these students, right? And so it's like, we got to help these guys because their heads are going to explode. And Professor Gonzalez and I have been working on that and talking to Wally on and off about it, about how to think about how to help them. We developed a different spreadsheet model for the value stream map that uses the one-piece flow system similar to my dissertation, and then shows that you can cut the hours down substantially by having a filtering system for the interrogatory. Okay, anyway, this is got his master's in manufacturing engineering. He was working at Artisan Industries, I think, in Waltham. And he, what do you got for a project? Well, you know, we bought a robot and they want me to be the person responsible for getting it up and running. And so what's pretty interesting is that he was not necessarily involved in the purchase of the robot and what to buy, because I was used to be a company owner and I'd say, I want to buy that. That's what I did. Hopefully I did a good job in my head of how to justify it, right? But once it shows up, everyone else at the shop needs to make the thing work and make money, right? So they sent him off to Japan to look at the thing while it's being put together. Then he comes back. And the goal of the capstone was actually to avoid a long learning curve on installation, right? Because the decision already been made that they have this robot coming. So I asked them, you know, what is going to be the thing that is going to cause Artisan all this heartache that they're losing their shirt putting this robot? And he spent basically 90% of the time on that MFE capstone on trying to figure out what is going to prevent them from having that robot come in and perform at a very high level right out of the gate, right? And so you've got a lot of coupling going on in this. Now, everybody knows about this coupling. The person that's going to be putting the spools of wire in the robot, they know that maybe there's a couple of bad things happening here. Someone in the office doing engineering knows this. You've got someone in the shop floor that's going to take care of the robot after the fact. But no one sees this all put together in one place and said, we really have a very interconnected system that if we don't understand it, it's going to cost us a lot of money learning about how to understand it. And can we head that off at the pass? And so that was a really major value that came out of his project. Now, another one I have going on, or no, this we just finished, Michael Wilkinson, just graduated last year. He's working in a place where they're putting integrated circuits on boards, and then there's an aqueous wash that goes on the board for cleaning, but the components don't like to get wet. It's like, okay, when engineer designed that, let's take chips that don't like to be wet and then put them in a place and make them wet. Okay, well, maybe it's the only chip in the world, and it's a government secret thing, and you got to use that chip, right? So now he's got this real problem of how do we wash the board and not mess up the chip, but be able to have the chip be able to fix the board, right? So, so when he decomposed the system, he's pointing out the fact that there's this coupling between these two DPs, the surface mount install, and then this process to maintain the reliability, and how they're managing that is where all of this expense is coming from. So maybe, you know, 1 out of 2 boards gets tossed because of the way that they're managing this surface mount installation problem. Cool MFE capstone by him because and he took this on by himself. I didn't suggest that he did this, but this is a serious problem at where he's working. And he ran a coupling matrix on 8 different solutions to the problem to see, could he identify what would be the optimal, maybe less expensive, fastest, or most reliable way to do it. And then when he goes to management, said, I want to spend $1 million and put this thing in over here in the shop. He's got all this backup to say, I've looked at the problem from underneath and from looking down and from the side. And I've worked out the interactions because is this $1 million problem at their company? I mean, it could have been. So it's worth it to do it. And I was very pleased to see this level of examination on what is ostensibly just an academic exercise, right? But it is important to the company. This is one I have going on currently. Brian Wilkinson, and hopefully he'll finish it by the end of the term. Some Raytheon division here in Mass, they're building a device, a vehicle. I'm gonna say maybe it's a rocket launcher. I don't know, something like that, right? Big, heavy components, big torque values. And the government says you gotta have 650 foot-pounds on these big bolts that hold the wheels on, presumably. Or a resilient part against the firing of whatever's coming off this thing. I said they really gotta have them be tight. And so they take the bolt, take the torque wrench, crank it up to 650, go back a week later, they're not at 650. Okay, so what happened? Well, was the torque wrench calibrated improperly? Does the actual device, I've never even seen a torque wrench calibration thing until he emailed me a picture of it. How do you calibrate the torque wrench calibrator? Does that go back to the National Bureau of Standards, or is it a homegrown test where you screw it to the wall, put a beam on it, and hang a container and pour sand into it, and until you can get the right moment on and see if it turns? I don't know. And then I said, well, what bolts are any good? Well, Raytheon bought them. That doesn't mean anything. You could have bad metallurgy in these bolts. They could be stretching. They could be designed to stretch, where you put them in, sink them, let them settle, and then come back and finish them. And they don't know. And this is costing them a fortune. They are not shipping stuff out the back door because they go to put it on a truck and send it away. And guess what? The bolts are put on. Pull the thing back, cancel the shipment, go get the torque wrench. So this is ongoing. And I shared this with my quality class. I said, this is a really cool problem because I've never actually come up against anything like this in my career. And so he's decomposing. How is it that these bolts can fail? Very, very cool. And I hope that maybe by the end of B term, I can share with my students what the outcome of this thing, because I can't wait to find out, you know, why they torque the bolts up, and then 2 weeks later there's some different torque value. I don't get that, right? Does that happen in your automobile engine? When they put my engine together 10 years ago, and they go and check the torque, I'll bet you it's the same as the day they put it in, or pretty close to it. It hasn't gone down 30% like this. Otherwise, your heads be leaking, you know. Okay, this is another live one I have going on over at Methods Machine. They build custom built machine tools. Ryan Louisi is doing this one. And so this is a person that has had me in classes in undergrad. He's in this very busy manufacturing company building these custom machine tools that respond specifically to some customer processes. Very cool businesses to go over and look at. And what they find is the machine tool is ready to ship, and they find that it doesn't meet the customer specs. It, could be the speed is wrong, some accuracy on how it's doing machining, whatever it's doing, and then have to stop and then go back to engineering and ask questions. Why doesn't it work right? And then engineering could have specified things before it went out to manufacturing, but for one reason or other they didn't, or they forgot, or they're lazy. And now it's getting ready to go out the door and it's not ready to go. And now it's going to go back. You've got this, one thing that Nam Su talked a lot about when he developed Axon Design was reduce non-productive iterations. Non-productive iterations cost you an arm and a leg. So now we're ready to ship the machine out the door, and we can't do that because we'll go back and find out. So this young guy, Ryan, charged by the head of engineering, go and figure out why we're having this communication problem between engineering and the guys in shop floor putting this stuff together. And so he's learning axiomatic design as he goes. But I said, Ryan, when you ask people in general the engineering manager, the engineering department, people on shop floor, vendors, whoever it is. You're gonna ask them a question and they're gonna give you an answer to the question, and it may not be a real exact answer because they're answering you what they think you asked them, not what you actually asked them. So you're designing this fix for this communication problem in this manufacturing system. And the people you're talking to already have biases about why they think it doesn't work the way it's supposed to. And they respond to you that way. So when you go to craft a solution of how to fix it, 6 months later, you got to do it all over again because you actually missed the essence of what was causing the problem, not what they think is causing the problem, what's causing the problem. Classic issue in industrial engineering. If you're going to go look at a shop floor, if something's going on, watching people making things, and you show up with your clipboard and stopwatch, which is the classical picture of an industrial engineer. As soon as you look at someone, they're going to do something different because they know you're looking at them. So if I want to know that Chris is sleeping, I'm going to go look at Adam. Right? So I said to Ryan, if you want to add value to Methods Machine, understand what's actually happening, not this perceived notion of it. Time. Some of the people he's talking to are not happy with him. They're like, I already answered this question for you. Yeah, but I talked to the other guy down the end of the hall and I came back and I said this, right? So I am really looking forward to what the resolution is because he's been charged by the engineering manager to solve this problem. So this I haven't talked to him in about 3 or 4 weeks, and I'm going to see where he's at going forward. These are the DPs that go. Tom, Professor Brown, right? And I remember this was pretty important. That what happened? Okay, current slide. All right. Chris said something. He said that if you find new ways to fulfill functional requirements by some method that have not been done before, you got a patent. And I tell the undergrads that, why does this actually make this stuff matter? There's a lot of them like, I'm an IE, I don't care about this. Because if you can find a new way to do something to achieve a goal, it can be very lucrative for you because someone hasn't accomplished that in that way. And I've always remembered that. It can also be really tedious to work through customer needs, functional requirements. That should say design parameters, sorry about that. And then process variables constraints. And all this extra effort may end up being valuable because you solved an issue that is potentially very lucrative and valuable to somebody else, right? So I don't know how many times students come to me and they go, well, we did our decomp and we have 2 FRs. Really? Well, I have the grade for your MQP. It's 0. Oh, why? Because you can't do this in 10 minutes. Will you please come back like you actually care and you don't want me to tell you to get a new advisor? Because that all shakes them up. Then they come back up and say, oh yeah, boy, there's a whole bunch of things. We always want to just jump to the solution. And decide what customers want before they ask them. Chris, right? We heard that before. So anyway, this is just a little bit of a look into my world on how I'm using this stuff. The undergrads need to be exposed to it in the classes and definitely in the MQPs. My grad students have done really awesome stuff, right? Because it's usually some real financial problem that they're responsible for. And Gabby's working on one for her own dissertation reviews. I didn't put any of that stuff up here. So that's pretty much it. Would you like to list out all the things that I was wrong about?
No, that was
It's too long, I know.
I mean, you don't have to blame all this stuff on me.
Reason that I use all this.
I just want to add that this is actually, against some values for sure. involve the project execution. So, how to meet your device. We were looking at the additive manufacturing process of ceramic materials, and our student actually used the whole process system and variables. And what are the main kind of variables that we need to actually work and focus on to convert the whole process from an open loop process to a closed loop process, so we can have adaptive control to improve the quality. Without the tool, we couldn't never. It took a while for us to really fully understand, what's in play, all the factors are in play there, and to really understand what is the goal we're trying to achieve, and what are the important factors actually contributing to the goal, and the ones that are the first step to focus on. But it was tremendously helpful, and we published a very good paper. And the process is my problem with it. Like 2 papers on this. The first part is about decoupling the whole system and trying to understand. So use that information to enable us to do the technical part, implement what we understood. We got the implementation part published.
Share with people when they first look at this, I say, we actually all use this method.
Exactly.
Always.
Yes.
We just didn't know that it was a formal method
Yeah.
until we learned about, non-soup, right? It's not a stretch to say, if you're a good engineer, I'm trying to think of all the things, right? and
Yeah.
What affects me.
Yeah.
But
So,
I've been very blessed and fortunate that I've had this, a lot of students get their PhD and they graduate and they go away. My PhD is my bunch 50 feet away from my office. So we've had this very long conversation going on for years about this stuff, and I just feel very, very fortunate.
I feel very fortunate that I was introduced to the tool by Professor Brown, and I just found it very useful when you're trying to really understand any manufacturing processes.
Gratifying to hear this. I introduced this 32 years ago. Came here and I said, what is the most valuable thing I can class that was at class before the class was over. Grateful that Sue was so supportive of this, but now got some tough. Walter Abel, and so boy, I can't. And so many people in the industry actually. As soon as I say axiomatic design, I don't want anything to do. It's very strange.
Chris, you've been because the industrial engineering department on the last ABED visit was the only department that was credited that had evidence that they taught design theory to the engineers.
Mhm.
And it's not anybody's fault. We're a big department. There's a lot going on, and they assigned me a TA for the 520 class who had not taken it.
What do you
So your decomp there where you say get TAs. Somebody in the administration has the time to do a good job. In order to do research and bring in more research, we're ignoring the fact that we've got to manage.
Yes, Master,
TAs.
I understand completely.
And since then, it's been a panic to hire somebody who could bring in more research funding.